Oh, that appears to be working well. Okay. Good morning, guys. I'm actually coming to you today from my new place. So I am probably going to, I'm using my phone's hotspot right now because I don't have, cable folks couldn't make it out over the weekend. And in order to make sure I don't accidentally go over any sort of throttle caps that may exist on my account, I'm going to turn off the video here, but then I will be using the screen share and the normal document camera software. So here we are. Which appears to be working. So today is our review day, right? Exam 1 is Wednesday. And that means today is your day to ask questions. We can run this any way you guys want. We can solve homework problems. We can solve some study guide stuff. I would prefer to not solve much study guide stuff. Let me go ahead and get some announcements down, and you guys can dig through the homework or any questions from lectures in the past that you would like to look at more carefully. If there are study guide problems, we can talk about those and I can solve related problems, but I won't be solving the exact problems from the study guide, because the purpose of those is to show me what you know, and that way I can give you some pointed feedback. Who is this? Give me 1 second. Sorry, I'm trying to do all sorts of stuff here. Hello. Oh.
Noon. To confirm your appointment, press 1. If you are no longer
yes.
carefully monitoring coronavirus guidelines from health
All right.
government officials in your area. For your safety and the safety of our technicians, we may or may not be able to enter your home or business. If we are not able to come inside, we'll do everything we can from outside using mobile devices and other virtual tools. You may be asked to perform some tasks, but our technicians will assist you and ensure your services are up and running. Thank you. Your appointment has been confirmed.
Okay. Sorry, I had to confirm an appointment with the cable guy. So if you guys could, please, in the chat, type the problems from the homework or wherever that you'd like to see. Like if you want to see homework 5, problem 2, type homework 5, problem 2. If you want to see study guide 1, problem 3, type that. That's the thing. And then I'm going to go through them in the order that they are presented in the chat. All right, so yeah, just like Trevor's doing there, please go in and type out those problems. That way I have an order to run through them in. Oh, God damn it. I just puked behind the couch. Yeah, so anything you guys want to talk about, type it in the chat and we'll go through it in order there, okay? I'm gonna cycle over here and pop open the homework. Just got this homework. No, Kitty, you're gross. You can't throw up behind the couch, Kitty. It's disgusting. All right, so I'm gonna start here and we'll just cycle through until we run out of time doing as many of these as we can. They tell us f of pi over 3 is 3. F primed of pi over 3 is -7. F of pi over 3 is 3. F primed of pi over 3 is -7. And then they're asking if g of x is f of x times sine of x, and h of x is cos x over f of x, can we find a couple derivatives? They want us to find g primed of pi over 3 And in part B, we want us to find h primed of pi over 3. All right, just looking to see if there are any sort of quick questions there that I should answer. Okay, no, we're good. All right. So can anybody help me with the problem we're looking at here? What's the idea? In part A, yeah, if I want g primed of pi over 3, how do I do that?
Isn't f of g of f prime of g minus g of prime?
Something like that. So it's for part A.
Do you use a chain rule for that?
I don't think we need a chain rule because it's not f of sine of x. So let's calculate g primed of x, kind of like Robert was saying, and I suspect that's what sorry, I don't have to mess up. It sounded like Trevor was saying. But yeah, we're going to calculate g primed of x sort of symbolically, right? Even though I don't know what the derivative here is, I can calculate in terms of the prime notation. So this is going to be d dx of this stuff. Right? If g of x is f of x times sine of x, then g primed is the derivative of f of x times sine of x. And now this derivative right here, that's a product rule thing, right? Because the function g is defined to be a product of f, whatever this unknown function is. I don't know exactly what it is, but I know it's got a name f, so I can work with that, and sine of x. So here's like my little f and my little g. You can kind of think of it that way, but I would be careful with the labels you use because the symbol g is already being used for something else here. But you know how this works. You differentiate the first thing. So I'll write this as f of x primed times sine of x, leaving the second thing alone, and then you leave the first thing alone, and you differentiate the second thing, right? This is the normal product rule. The sort of weird thing here is I just don't know what f is, so I don't know what f primed looks like, but I can write it all out. The derivative of f, that's f primed of x, this is f primed of x times sine x, plus f of x times the derivative of sine x, which is cos x. Does everybody see where this formula is coming from? Product rule. So g primed of pi over 3, if this is g primed of x right here, then g primed of pi over 3 is what I get by plugging x equals pi over 3 everywhere in this. So that's f primed of pi over 3 times the sine of pi over 3 plus f of pi over 3 times the cosine of pi over 3. Now I have to look and see what information do I know? What information am I relying on them to give me? Certainly the sine of pi over 3, I know this. What is this?
Square root of 3 over 2.
Excellent. And the cosine of pi over 3, what is this?
1/2.
Good. So this is f primed of pi over 3, which is -7, times the square root of 3 over 2, plus f of pi over 3, which they told me is 3, times 1/2. And you could stop here if you wanted to. There's no reason to necessarily simplify beyond this, but you can simplify beyond this if you like. This is -7 root 3 over 2 plus 3 over 2, which is -7 square root of 3 plus 3 over 2, if you really feel like it. Right, this is a really good problem, and problems of this sort do have a tendency to show up on tests. Are there any questions about this problem? Okay, let's look at part B. I'm going to cover this part A solution so we can do part B here in a second. So does anybody need more time on part A?
I have a quick question, Professor.
Yeah. Yeah, go ahead.
Okay, for the product rule that you used like in part A in the beginning, like I've seen different videos and explanations where they do f of x and then they do g of x prime plus g of x f of x prime.
Yep.
Like it's the same thing, right?
Yeah,
Right.
that's exactly what we're doing here. Yeah, it just
Okay.
depends on the label you choose for these things, which one you want to call F and which one you want to call G. But the idea is you
Right.
differentiate one, leaving the other alone, and then you add that to what you get when you swap the rules around. So like differentiate one at a time. Here I differentiated the first and left the second alone. Here I left the first alone and differentiated the second. It doesn't matter which one you call F and which one you call G because they're being multiplied, and the order,
Right.
order of multiplication doesn't matter. As long as you differentiate the two pieces one piece at a time and then add up those two little products, you'll be good.
Right. Okay. Thank you.
Any other questions on this? That's a good question. So like, does order matter in the product rule, or do the labels matter? All right, then we're going to charge ahead here. For part B, we want h primed of pi over 3, and h of x is this cos x divided by f of x. So h primed of x is what we get when we differentiate all that. This is going to be a quotient rule derivative. So we'll have the bottom times the derivative of the top. Minus the top times the derivative of the bottom. All divided by the square of the bottom. Right, that's my quotient rule. And the mnemonic there is low d high minus high d low over low low. But hopefully you guys have all got that baked into your skulls by now. If not, you may want to make some flashcards with that mnemonic or something, because it's important to remember the quotient rule, and I know it's a tough one to remember. So now I'll fill in all the little bits. This is f of x times the derivative of cosine is negative sine x. So I'm going to put the negative out here and write it like this. That's f of x times the derivative of cos x, f of x times negative sine x. I'm writing it as one piece like that. And then we'll have minus cos x times the derivative of f of x. Well, that's f primed of x. And all of this is being divided by f of x squared. Really can't do much with. What are you freaking out about, Bubba? Oh, cable guys here. All right. So if I want h primed of pi over 3, the move from here is to plug in pi over 3 for x. This is h primed of x right here. So h primed of pi over 3 is going to be negative f of pi over 3 times the sine of pi over 3 minus the cosine of pi over 3 times f primed of pi over 3. And all of this is being divided by f of pi over 3 all squared. It's all right, Hamlet. And now I have to turn back to what they told me about the function f, right? The sine of pi over 3 and cosine of pi over 3 showing up again. I know these. Sine of pi over 3 is root 3 over 2. Cos of pi over 3 is 1/2. F of pi over 3, if we look back up here, f of pi over 3 was 3. So this piece right here is 3. And f primed of pi over 3 is negative 7. So this piece right here is a negative 7. And down here, f of pi over 3 showing up again. That's going to be 3 squared. So I'll plug in all the bits. this is, I've got my negative here, so -3 times the square root of 3 over 2 minus 1/2 times -7, all divided by f of pi over 3, that's 3 squared.
Why did that f of x up top become negative? I think I missed that.
Remember, that's the derivative of cosine here. We needed to differentiate cosine. The
Yeah.
derivative of cosine is negative sine. So I just put the negative out front this whole chunk.
Okay, all right.
Yeah, fair question. So the negative is really attached to the sine, but they're multiplying. So I can just think of that whole kind of monomial as being negative. Okay. Is there much to clean up here? Not really. Again, we can simplify a little bit. This is -3 root 3 over 2 plus 7/2, and this is all over 9. Remember, with fractions, we always think of the top as being in parentheses like this. And you can combine these two into a common denominator expression. This is -3 root 3 plus 7 over 2. And really, when you divide that by 9, you're multiplying by 1/9. And so if you want this sort of as clean as possible, I would say it's -3 square roots of 3 plus 7 over 18. I wouldn't try to simplify it beyond that. And again, if you're wondering, where would I be okay to stop on the test? Like if I'm really short on time, I'm on the test, I want to know where can I stop for full credit? Right here is fine. Right, if the problem is just asking for this, this would be a fine place for you to stop. No need to go past there. You would need to fill these in. I do need to know that you know what the cosine and sine of pi over 3 are. But once you got to this line right here, you would be okay to stop. All right, in the interest of using time, I'm going to move to the next question, unless there are any questions on this. Any questions on what we just did here? Okay. Alrighty. So Mackenzie asked, that we have to know about definitions and whatnot. What sort of definitions do we need to know? Well, you need to know what it means for a limit to exist, right? You need to know definitions to be careful with. I mean, certainly all of them, but limits existing definition. You need to know the definition of continuity. Like at some number A. You need to know the definition of differentiability. Other things along this line, definitions and theorems, you should know the statement, you should know the squeeze theorem. And you should know our theorems on continuity. You should also know the limit laws. These are the sort of basic things. Now, most of this stuff, if I was going to ask you questions about this sort of stuff, would show up in true-false questions or multiple choice questions. Like true or false, if you're continuous at A, then you're differentiable at A. That, for example, is false. Or I could ask you, is this inequality enough to guarantee this limit by the squeeze theorem? Those sort of things. Give me just one moment. The cable folder just showed up. Oh, Hammy, watch your head. Watch your head, bud. I don't have a mask on either. Hi, man. Yeah. I don't have a mask on right now. Are you comfy coming in?
I'm just required to wear one. Oh, the dog's fine.
He's a nice guy. Yeah. Just let him smell you. He'll be friendly. Oh, now he's looking for a cat. Henry, come here. Stay inside, Bob. Come on. Right, sorry, I'm actually a teacher. I'm in the middle of the class right now. So if you don't mind, feel free to poke around. There's coax is behind these boxes here. And also in the back left bedroom. Right now I've got the cable modem in the back left bedroom. I can show you. The other coax jacks.
The modem in here.
So I've got one coax here, but right now I've got everything set up back here. So if it's possible to get it set up.
So you'd like it out here.
I don't have a
Where are you going to work?
probably right out there. Well, actually, I don't have my. This is actually going to be the office. So we'll have.
I would suggest put it out there. There's a really older line.
Okay.
And you might have drops with this cable.
Okay.
We can do that one, yeah. We can do this cable line.
Okay.
Right.
There's a newer one. Sorry, there's a newer one like that out here behind these boxes too. But if you think that it would be wisest to do it out here, we can do that.
Because you don't have a dish or anything like that.
No, I think the guy living here before used the dish.
All right.
But because I have to keep them on, I need something that doesn't go out in the rain. If we hike that last box out of there, that should reveal the coax. And it's just
Okay,
get that one there. Yeah, so this might be the perfect for this.
Let me take a look outside of there.
Okay, man. Yeah, if you need anything, just holler. Okay, sorry about that, guys. So yeah, definitions and theorems you need to know are right here. How do we know when to use the squeeze theorem? So look at the homework problems and look at some of the textbook problems that relate to the squeeze theorem. The squeeze theorem is useful pretty much only when you have something that's like oscillating a lot, like a cosine of 1 over x or something that's bouncing back and forth, but also has a function bounding it. So where were we? That was here. This is in here. So if you look at the sort of examples where we use the squeeze theorem, it's always something like this, like x squared times the sine of 1 over x, something along those lines, where the graph oscillates really quickly, but you also have some other function multiplying that kind of drags you down to 0. So if you're a little bit nervous about the squeeze theorem, my suggestion would be to come into the textbook here and look at some of the problems related to the squeeze theorem. There's actually a bunch of them. Here we go. So starting right here, 35, 36, 37, 38, 39. In section 2.3, 35 through 39, these are all good squeeze theorem problems. And what you'll notice is consistent about all of these, they have something that allows you to set up an inequality. And if you try to take the limit just by plugging in, shit doesn't work out nicely. For example, if you look at number 36 here, you've got this sine of pi over x, and you're trying to send x to 0. So you know that the sine of pi over x is going to misbehave near 0. It's going to oscillate really rapidly, like the sine of 1 over x does. But then you've also got this function out front that hopefully is going to drag it down. So those are the situations where you will need the squeeze theorem. Anywhere you could readily establish an inequality. All right. So those are the definitions and theorems I would be most concerned about, these guys. Holly wants to look at number 15 from the study guide, so I'm going to pop that up. And I won't do that exact problem, but we'll do a related one. Okay. So this is study guide 1, number 15. I'll write it down, then we'll tab back over. Let's say find the derivative of, and I'm going to use something else. I'll say f of z is e raised to the power of. I don't know, z over z squared plus 1. Okay. Same sort of idea though. You've got a composite function. The inner function here, so this is a chain rule thing. My inner function is the z over z squared plus 1. That's u. And my outer function, f of u, is just e to the u. So you see how if you plug this in here, you get our function? So if I want to calculate the derivative, f primed of z, what I need to do is differentiate the outer, leaving the inner alone. If I differentiate like e to some stuff, I just get e to that stuff back. So this will be e to the z over z squared plus 1 times the derivative of the inside. So I have to multiply by the derivative of z over z squared plus 1, which I'll just write as a prime like this. Now that inner derivative requires a quotient rule. And it's a little bit complicated having a quotient rule inside of a chain rule like that. But if we take our time, we can do it. It's nothing special. The e to the z over z squared plus 1 piece is just going to hang out. And now over here, to figure out my quotient rule derivative, I'm just going to open up a big bracket, give myself some space to work, and make clear that these things are multiplied. I know how my quotient rule works. I take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So I'll write that out schematically. The bottom, z squared plus 1 times the derivative of the top minus the top times the derivative of the bottom, the derivative of z squared plus 1. And then this all goes over the square of the bottom. Okay, so I've got my original function, e to that stuff, right? Because that's how the chain rule shakes out, times the derivative of that function. And here's the quotient rule derivative of the inside. So this is differentiating the outside, leaving the inside alone, then multiplying by the derivative of the inside. This piece isn't going to change, but this piece I need to go ahead and figure out the derivative. So I write that out schematically using the prime notation. Annie, come here. Come here. Lay down. I love you, bud. Lay down. Stop scaring the cable guy. So now we just need to punch out each of these little derivatives. It's complicated, baby. The neighbor cat is out there. The cable guy is here. You might want to put on clothes before coming out, just FYI, because again, the cable guy is here. So the derivative of z here is 1. So this is z squared plus 1 times 1 minus z times the derivative of z squared plus 1 here is 2z plus 0. The 1 differentiates to 0. And then we're dividing all of this by z squared plus 1 quantity squared. And again, if you're wondering where you could stop on the test, what's the minimum we could do? It's this. If you get to this line and stop, I'll be like, okay, that's fine, that's correct. Is it as pretty as it could be? No. But is it correct? Yes. And if you want to prettify it a little bit, then we'll have e to the z over z squared plus 1 times, let's see what we're going to have in here. This piece is just being multiplied by 1. So it's going to stay z squared plus 1. And when I multiply by that 1, the parentheses are going to go away. So I'll have z squared plus 1 minus 2z squared from this other piece. And z squared minus 2z squared, that's minus z squared. So I would write this as 1 minus z squared over z squared plus 1 quantity squared. And that's plenty nice. Doesn't get much nicer than that.
I'm kind of confused with that one. When you multiplied it with z prime, where are you getting that z from?
So this piece right here is the bottom times the derivative of the top. The bottom times the derivative of the top. So I would think of this piece, here's a little trick for product and quotient rules. Instead of using f and g, use u and v. That way, inside a problem that already has f's and g's, you can sort stuff out. So this is low times the derivative of the top, low d high, minus high times the derivative of the bottom, high d low, over low, the bottom squared.
So you don't need to get the derivative of e to z over z squared plus 1.
Well, we did. So that's differentiating the outside, leaving the inside alone. So it's a chain rule thing. The derivative of e to the u is e to the u, right?
Oh, okay, yeah.
So remember, if f of x or whatever is e raised to the u of x, where u is a function, then the derivative f prime, no Hamlet, is e to the u of x times u primed of x. This is by the chain rule. So the exponential stays there, right? Just like when you differentiate e to the x, it stays e to the x. When you differentiate e to anything, that piece will always stay. But then you have to multiply by the derivative of the inside. So the derivative of e to the complicated shit is e to that complicated shit times the derivative of that complicated shit, or e to the u times u prime.
Okay, thank you.
Of course, yeah, this is a challenging problem, but it's only challenging in that the little quotient rule derivative you need out here is kind of weird. Besides that, it should be very reminiscent of a lot of other chain rule problems. Other questions on this? Shut up, Cortana. Other questions on this? Yeah, if you want to, Ronald, yep, you can write it like that. That's true. As long as f is your lower function and g is your upper function. So here the labels matter because we're subtracting in the top, right? If you multiply two things, it doesn't matter what order you multiply in, but when you divide two things, it does matter what order you divide in, right? 5 divided by 2 is not the same as 2 divided by 5. So the quotient rule is more sensitive to your labels, more sensitive to order than the product rule is. So Ronald, when you ask, can we write this formula as f times g prime minus g times f prime? It depends on which one is f and which one is g. That's why people like this mnemonic low d high minus high d low over low, because it kind of assigns the right guy in the right spot without thinking too hard. Does that make sense?
So does
Right,
low
so as
always
long
go-
as I,
I'm sorry, let's let Ronald answer real quick and then we'll go over.
I was saying, right, so as long as like I'm thinking the right top or bottom, like it should be fine the way, like which one I prime.
Yeah, as you typed it there, f times g prime minus g times f prime, try to compare that to
Yeah.
what we have here. So the only way that works is if, let's see, so f would have to be your bottom function there and g would have to be your top function there. That formula works fine for the derivative of g over f. Right? Usually people write it as f over g, that's the only reason I'm pestering you to say you got to be really careful about your labels. So what you wrote down is the numerator of the quotient rule for the ratio g over f. Is that making sense?
Right. So I would have to do it the other way then, just to get the normal one.
I would recommend writing it the other way. Yeah, that way
Okay.
always look the same and they'll like click in your head. You know, if you tie your shoes different every other day, it's harder to remember, that sort of thing.
Yeah.
All right, what was the other question? There was another question being asked.
I was just gonna say that does it matter which one you multiply? Like, if you put u prime times v, there's no difference, right?
It does matter. So you're talking about for the quotient rule, right? For this?
Yes.
Yes, it does matter. If you swap this, if you mean like v times u prime or u prime times v? No, that's fine. That's fine. Yeah. Like within each of these little pieces, does the order of multiplication matter? No.
Yeah, that's what I mean.
But the order of subtraction upstairs overall does matter. If you
No, yeah, I know the subtract.
Okay, I
subtraction
get you. Yeah, no, if you wanted to write this as u prime times v minus v prime times u, that would be okay.
Okay.
All right, I'm gonna charge ahead so we get to some of these other questions. But if you do have other things that you want to ask, be bold about it. I'm gonna try to look through the chat for questions, but mostly I'm just looking for problems there. So if you want to ask something or you want to insert a comment, just hold down the space bar and talk like a walkie-talkie. Don't be shy. So homework 5, we've got a few requests here from Robert, 23, 35, 28, and 29. I'm going to try to be diplomatic about this. Are there any that were requested multiple times? Homework 5, 14. No. Okay, Robert. So I'm going to do 23 and then I'm going to cycle through and then we'll come back to 35, 28, 29 at provided time. All right. And this is kind of similar to one that was asked in the chat down later. So here we've got the derivative of e to the 8t times the sine of 2t. And again, this is a chain rule thing. So this is homework 5, number 23. Find capital F primed of t, where capital F of t is e raised to the power of 8t times the sine of 2t, like so. All right. Again, chain rule. And again, inside the chain rule, there's another little thing going on. This time, instead of a little quotient, it's a little product. So I recommend, if this is looking weird, spend a second identifying your inner and your outer. Our inner function u and our outer function f of u. The inner here is the exponent, 8t times sine of 2t. And our outer, just like in that last problem, is e to the u. Right, so what I've got here is e raised to a bunch of variable shit. So I'm thinking of this as like e to the x, but instead of an x, I have a more complicated function on the inside. So in order to differentiate, capital F primed of t is going to be the derivative of the outside with the inside left alone. So I differentiate the outer function, which is like e to the u. E to the u differentiates to e to the u. But then I need to multiply by the derivative of the inside. Which I like to write out like this. And just like that last problem we did, where here we had a quotient and needed a quotient rule, here we have a product and we need a product rule. So this is going to be e raised to the power of 8t times the sine of 2t times the derivative of this. And this, again, a nice trick is to think of this as like a u times v. So I'll have u primed, and I'll write it all out schematically here. Maybe I should put this in a bracket just like we did the last one. This will be the derivative of the first guy times the second, plus the first guy left alone times the derivative of the second. And we've actually got a little chain rule buried all the way down in here. You see, when we take the derivative of the sine of 2t at that very last part, we're going to need another little chain rule there. Questions so far? All right. So the derivative of 8t is 8. So this first piece is 8 times the sine of 2t plus, and then I'll have 8t times, I need the derivative of sine 2t. And this again is a little chain rule thing. So we got to think about that. Can somebody help me with the derivative of the sine of 2t? This is a fairly simple chain rule. I'm just asking for this piece.
Is it 2 cosine 2t?
That's perfect. Yeah, beautiful. How did you get it?
So you have to like take out the inner number first and it would go on the outside, and then you just have to know the derivative of sine.
Yeah, I mean, that's true. That is how sine and cosine derivatives always work. The explanation there a little bit, if we differentiate the sine on the outside, leaving the inside alone, we get a cos of 2t. And then we'd have to multiply by the derivative of the inside. The derivative of 2t is just 2. And so what Ronald said there is 100% true. Anytime you differentiate like sine of at or cosine of at, differentiate the outside like normal, and then the result is going to be you'll multiply by the number there. If the inside of the trig function were more complicated, we would get something a little more complicated, but it is kind of worth remembering on its own because those things show up so much, especially if you intend on taking physics with calc. So altogether here we have 8 sine of 2t plus, I can multiply these guys and get 16t cos 2t inside my bracket here. So that is the full derivative. How are we feeling about this? Okay. All right, and then Robert, I know you had a few other questions. I'm going to cycle through and try to give everybody a chance. And if we have time, we'll come back to the others. Madi wants to know if we can go over the rules with the definition and an example. Madi, what exactly are you asking for there?
I just was like in the tutoring, and I was getting confused with the chain and the product rule to use them for each one, because like my tutor kept on saying the chain and then they would switch. So I was wondering if you could just clarify each of them.
Yeah, sure. I mean, I can write down what they say. So here we actually use the product rule within the chain rule. The chain rule is kind of the big daddy of all differentiation rules. It says if your function is a composite function, let me write it like this. If capital F of x is little f of little g of x, then the derivative of capital F is little f primed with g of x inside left alone times the derivative of the inside. And the way everybody remembers this is you differentiate the outer, leaving the inner alone. And then you multiply by the derivative of the inner. So if you want to look at another example, kind of in addition to the one we just did, something a little simpler. If I wanted to differentiate something like the cosine of x cubed, the way I would do that is by differentiating the outer. My outer here is cosine, and leaving the inside alone. So the derivative of cosine is negative sine. And if I leave the inside function alone, that's going to be negative sine of x cubed. And then I multiply by the derivative of the inside. So this is like my first piece. This is like my f primed of g of x. And this is like my g primed of x. The product rule is very different. The product rule tells us how to differentiate two functions that have been multiplied together. So if we have, I'll hold here for just a few seconds if you're still writing. 4, 3, 2. All right. Product rule tells us how to differentiate two functions that have been multiplied together. So if we've got something like I have like f of x times g of x, and I want to prime that whole thing. I want to differentiate a product of two functions. The way I do that is by differentiating them one at a time. This would be f primed times g plus f of x times g primed of x. I differentiate one function in the product at a time, and then I add up the results. So for example, if I wanted to differentiate like x cubed times tangent x, if I needed to differentiate that whole thing, I differentiate x cubed and leave tangent x alone. And then I add that to what I get when I leave x cubed alone and differentiate tangent x. The derivative of x cubed is a power rule thing. That's 3x squared. So that's 3x squared times tangent x plus x cubed times the derivative of tangent. Derivative of tangent is secant squared. So they both do end up involving some amount of multiplication, but they're fairly different rules. Does that clarify things a little bit?
Yes, thank you.
You're welcome. You're welcome. All right. Let's move on to the next thing that was in the chat. Let me see here. All right. Yeah, so I'm just going to keep rolling through in order here. We'll do as much of this as we can. That was the rules and examples. Homework 5, questions 4 and 20. So let me look at number 4 here. And if it's quick, maybe we can do 20. Otherwise, I'm going to have to cycle back around after other people have had a chance. 4, I hate to do this, but this is actually one we've done twice in class now. So I think it is best for everybody, including you, Alma, if you go back to the video from last Friday and watch that. Also, I think in the video from last Wednesday, we did that. I can set it up, but rather than doing the whole thing again here, I'll set it up for you. And then I'll say to finish this, go back to the previous video. That way everybody's getting as much time to see new stuff as possible. If f of theta is theta cos theta times sine theta. This is like a three-way product. So f primed of theta, I need to differentiate all this stuff. I need to differentiate theta times cos theta times sine theta. But the challenge here, of course, is that that instead of having two functions, like it says right up there in the product rule, I have 3 functions. And if I want to differentiate a product of 3 functions, I'm going to have to kind of partition it. Meaning I'll think of this as like a piece, and I'll think of this as a piece. Kind of like here's your little f and here's your little g. Or I'll call them maybe little u and little v. So that derivative should be u primed times v plus u times v primed, following the product rule. The challenge is that u primed is itself a little product rule. So u is theta cos theta. So this is theta cos theta, all primed, times v, which is sine theta, plus, and then u times v primed is theta cos theta times the derivative of sine theta. All right. So this is our setup. And then you're going to need another little product rule in here. We're working? Okay, awesome. Is there anything that we need to do, or did you have to run any lines? They said there might be a charge, like
Personally, I'm not charging them. If you do see any charges, just give them a call and tell them everything the issue was on the outside. It was disconnected on the outside.
That's dope. You're so awesome, man.
And they're gonna take that out of you. Those your Wi-Fi names and password.
Okay, are they new or are they the same?
If you were using in the
Yeah,
previous
it's old
others,
equipment.
everything should be the same.
Awesome. All right. If I want to change those, actually, I've been curious. How do can I change the password and stuff?
Once you connect to it, you just type the IP address of the modem, which is 192.
192.
.168.0.1. All right. Then it's going to ask for a username and a password, which is going to be admin and password.
Okay. No caps or anything?
Nope.
Okay.
And after that, you get into the interface, and it should be pretty straightforward.
That's so awesome, man. I really appreciate your help. You too. Okay, so yeah, I am going to leave this here. I recognize, as I said that, right, you can go back and watch the older video. I think probably the video from last Friday isn't up yet, but the earlier video is there. So we have done this a couple times. And from here, see if you can work it out schematically, or see if you can talk to some of your classmates and get them to help you through the rest of these steps. It's not too hard. You need a little product rule here. Ah, fuck it, let's do it. We're this close, right? So then here we've got another little u and another little v. If I want to differentiate this, again, need the product rule. So we're going to have theta primed cos theta plus theta times cos theta primed, all times sine theta, plus theta cos theta times sine theta primed. All right, and I'll leave it here because here we have everything we need. We just gotta take the derivatives. So theta primed would be 1, cos theta primed would be negative sine theta, and the sine theta primed out here would be cos theta. I'll let you finish it from there. Yeah, no problem, no problem. So as we charge forward, she wanted to see number 20 also. Let me take a quick look at that. Something I can do quickly. Solution in here. We want to find the derivative of this. I think I did see some other people asking for this, so I will go ahead and do number 20. Oh no, we're good. Okay, then I will go ahead and move on. This one is a product rule. Just for the record, you differentiate 5t, leave sine pi t alone, and then you swap the rules around and add those up. So if we move forward, squeeze theorem problem. We can look at a squeeze theorem problem. So sort of the classic squeeze theorem problem is a rapidly oscillating trig function. What can we do here? 0, 1, 19. Yeah, but that wouldn't work. So yeah, we'll need something like this. So find the limit lim x to 0, x squared cos 1 over x. All right, this limit is a challenge because the cosine of 1 over x, we can't just substitute in here. The challenge here is that cosine of 1 over 0, what the hell is this? Lim x to 0 of cos 1 over x. This does not exist because rapid oscillation. I can show you in Desmos what I mean. But yeah, so this piece on its own, this is a problem piece. Cosine of 1 over x is really badly behaved near 0. Specifically, I try to actually graph the thing. See, right, near 0, he does this like crazy rapid oscillation thing that some of these other functions we've been looking at do. Make it hard to figure out what's happening there. So if we want to figure out this limit, this is our challenge, figure this out. How do we do it? Well, by the squeeze theorem, if I'm able to sandwich this whole function, the x squared cos 1 over x, between two other functions that go to the same place, then I can take that limit. And the observation that lets us get started is that cos of 1 over x is always trapped between -1 and 1. So if I multiply through everywhere by x squared, I get -x squared is less than or equal to x squared. Cos 1 over x is less than or equal to positive x squared. And you remember how our squeeze theorem went, the limit of the function on the left as x goes to 0. This is, as x goes to 0, where does -x squared go? What's this limit?
0.
Good, yeah, x squared and -x squared are both continuous at 0. And the limit as x goes to 0 of the function on the right is also 0. So like
Do we,
policeman behind you, here's the policeman in front of you, and if they're both going to the police station, we, as the function in the middle, are also going to the police station. So we'd say therefore, lim x to 0, x squared cos 1 over x equals 0 also by the squeeze theorem. You see me abbreviate squeeze theorem SQZ. You're welcome to do that too if you want. But yeah, this is how the squeeze theorem problems normally go.
and we need to show those steps in order to get credit, right?
Absolutely, yes. The observation won't always be this, but it will often be something like this. So Trevor, if you look back at this graph, here's just cos of 1 over x, here's y equals 1, here's y equals -1. The red is always trapped between the blue and the green, right? How did I know that? It's coming from the unit circle. The cosine function is defined as the x value on the unit circle when you rotate theta around. So cosines are always between -1 and 1, no matter what's inside. This could be cosine of dog shit, or cosine of your mom, or cosine of the cat that's outside screaming at me because my neighbor or whoever hasn't been taking care of it. This could be cosine of anything, and it will always be no smaller than -1 and no larger than +1 because it's a cosine. Cosine of anything is always trapped between -1 and 1. And the same is true for sine. Some other useful bounds like that we know of are arctangent, right? The inverse tangent function is always trapped between -π/2 and +π/2. Any other bounded functions we can think of this way, but cosine and sine are the classics, and the range of cosine and sine is -1 to 1. They never get bigger or smaller than that. So we know to start here from the definition of cosine or from studying cosine graphs in trigonometry. And I know my goal is to make my function x squared times cos 1 over x show up in the middle. So to get towards that, once I have this, I know to multiply through by x squared because that will make my function show up in the middle. Once I do that, I ask, okay, well, here's the guy behind me and here's the guy in front of me. Are they going to the same place? So I take the limit of the guy on the left, see that he's 0. Take the limit of the guy on the right, I see that he's 0 also, which means the guy in the middle, my guy, has to go to 0. And if you want to see this whole thing graphically, squared, here's our function. I can fiddle with this a little bit. All right, here's our function. Here's my lower bounding function. That's the guy behind me. Here's my upper bounding function. That's the guy in front of me. So I have no choice but to go to 0 because the guy above me is going to 0 and the guy below me is going to 0. Does that make sense?
What if the number wasn't x squared? Like what if it was like x cubed? Would we still do the same thing?
Same shit works. Yep.
Okay.
Other questions on this one?
What if the number was like 2x, or like if it wasn't like an exponent?
Same thing. As long as you have a function that bounds you from above and a function that bounds you from below, and those two functions are going to the same place, then your guy doesn't have a choice. So let's look at a few examples. If I change the original function to an x cubed, it's not as clean, but we do still get the same sort of bounding things, right? You see the red function trapped in between these guys? Or if I change this to an x, oops, sorry, Desmos is not like that. And I change this to an x, and I change this to an x. This is going to be less obvious, but again, we get this sort of bounding, right? You see where the red function is trapped between these lines. Now, really, I should say my upper bound function here is like absolute value, and negative function here is an absolute value, but it still works, right? You see that these guys, the lines, which are, here, let me put them both in purple so you can make out the boundaries better. You can see that the purple bounds the red, which is what we need for the squeeze theorem to work. So it really does work well.
So is the answer always going to be 0, or if it's
Well,
not?
if you have a power function multiplying cosine of 1 over x, that will always tend to 0, but there are lots of squeeze theorem things that don't. If you look in the textbook, they have some examples of other things, and they've got some pictures that can help you see how it can work in other cases. I think they do. They certainly should. Yeah, here's sort of the general case, right? Now it turns out it's kind of hard to come up with creative examples here. It's hard to come up with examples that don't go to 0 unless you get a little bit silly, like using some of these 37, 38 problems. But as long as you understand the principles and you're comfortable working with the inequalities, you'll be okay. All right, let's see if we can get a couple more problems in here. I know we're getting close on time. Where are we? 10:33, yeah, we're getting there. Where are we? So we did these. Trent wants to see number 21, and then we're going to go to 7 and 6. So 21 is here. I'm going to find the derivative of the square root of x over x plus 7. That's a little gnarly. All right. So we need the chain rule here. The chain rule is the only way to attack this. My outer function is the square root function. And my inner function is this ratio, x over x plus 7. So I'd say, here's my inner, if we want to, here's my inner, x over x plus 7. Here's my outer, f of u is just the square root of u. And you see, if I plug this in here, I do get this. Now, I would recommend writing this as a power. That's how we differentiate square roots, remember? So this is x over x plus 7, all raised to the 1/2 power. In other words, when I go to differentiate my outer, I'm going to think of it as a power like this. And the result is y primed, my overall derivative, is going to be, I differentiate the outer, leaving the inside alone. Right, so if I want to differentiate some stuff to the 1/2, that's the power rule that I use to differentiate the outer and leave the inner alone. So the power comes down, and then I subtract 1 from the power. The inside stays the same. I don't do anything to the inside in this step. But then over here, I need to multiply by the derivative of the inside. That is how the chain rule works. And I'll just write that as a prime. Now, in order to finish things up, I need to calculate this derivative. I need to know what is the derivative of x over x plus 7. That's going to be a quotient rule thing.
Can't you also use the power rule here?
No. Not unless you can write this as a power function. So there's no way to write this as x to some power, right? You've got a big fraction here. The top is x and the bottom is x plus 7. So unless you can rewrite this as some power, what were you thinking? Can I look a little closer? I think you might be
I'm talking about just for the first part, the x over x plus 7 to the 1/2.
What about that? Okay.
Can't you do negative, or like make it over the exponent negative 1/2 because you subtract 1 and then you multiply the inside by 1/2?
Walk me through exactly what you're thinking. So tell me what to write.
Well, the power rule is you subtract the exponent by 1
Right.
and then you multiply the normal part by whatever the exponent was.
Yeah. So that's this 1/2 times this thing to the 1/2 minus 1, which is negative 1/2. Yeah, so the power rule is how we differentiate the outside. What do you want me to put in here?
The x over x plus 7.
Okay, good. And then what?
And then you multiply 1/2 by x over x plus 7.
This can't come inside. Because this power right here, powers don't, so it's an order of operations thing, right? PEMDAS?
Yeah.
This power takes precedent over this multiple. Here I've got a number multiplying a thing raised to a power. Now by the chain rule, we're not done yet. We still need to multiply by this, the derivative of the inside. But even as far as simplifying here, can this 1/2 come inside here? It cannot.
Okay.
The order of operations tells me that this power is in charge. The parentheses, then exponents, then multiplication.
Okay, yeah.
I have to deal with that. No, it's okay. It's all right. It's good. These are the sort of things that we want to talk about during the review, and it is very much worthwhile. All right. So that brings us back here. We've done our power rule derivative. That's good. That's the derivative of the outer, and we left the inside alone, but now we need to multiply by the derivative of the inner. And to take the derivative of the inner, we'll use our quotient rule. If we do want to clean this up, we can. I can write this as 1 over 2 times the square root of x over x plus 7. That's about as nice as I can algebra-wise clean up this first chunk here. But I don't know if that's any less scary looking than it was. And then over here, I need the derivative of this thing, which is going to be a quotient rule thing. So low d high, that's x plus 7 times the derivative of x minus high d low, that's x times the derivative of x plus 7, all over x plus 7 quantity squared. And I'll put this in some brackets too, like that. It's up to you whether you want to rewrite that first piece like this. You don't have to, but just to show you kind of why the algebra shakes out the way it does. This guy is really a square root and it's really downstairs. And then this guy is like 1/2 times that big fraction. So it would come out like this. And then this piece, however you want to write this, I might actually just leave it as it was the other way. I think it's a little bit simpler looking. This piece over here, the derivative of x is 1. So this is x plus 7 times 1 minus the derivative of x plus 7 is also 1. So just minus x over x plus 7 quantity squared. And then we can clean up the x minus x, those go away. So we'll get 7 over x plus 7 quantity squared. And if we were very, very patient, we could probably clean this up a little bit more. In here, I could take the square root of the top over the square root of the bottom. I could flip the fraction. I could maybe combine and cancel some of the powers of x plus 7 with this. But I think the fastest way to do it is going to be to just leave it like this and call it this. Rewriting this first piece in this way, there's nothing wrong with that. Certainly it's correct and it's the right way to read these powers and this multiple. But I would just leave it as it was here. I wouldn't bother doing this. That's why I went back to writing it like these.
Can you get the top part in the frame so that I can screenshot this?
Sure. Zoom out a little bit. Here we go. There's the whole thing. So 7, I think we might have looked at already. 6 and 7 are next in the list. See what we got here. So that's 7. Oh no, we haven't done either. Okay, we'll go ahead and take a look at number 6. This is a good product rule thing. And then number 7 looks like it's a tangent line problem. We can definitely do that too. These will probably be the last ones we have time to do right now. But I will have an office hour today. You guys can come by that if we want to see more problems. If I didn't get to your problem, I'm sorry. First, we want to find the equation of the tangent line to for e to the x cos x cos x at the point 0, 4. And they could have just said at x equals 0. Right? If they wanted to be ruthless, they didn't need to tell us this y value, but they're kind enough to do that. They could have just said, find the tangent line to this function at x equals 0. And we would have to figure out that the y value there is 4. Okay. The big thing here is we need the slope of the tangent line, which comes from f primed. Right? They gave us the point. So to find any line, you need a point and a slope. Here they gave us the point. We need to figure out the slope. The slope is going to come from the derivative. So if I want to take the derivative of this, that's d dx of 4 e to the x cos x, which is a product rule thing. I can think of this as my little u and this as my little v. So this is going to be 4 e to the x primed times cos x plus 4 e to the x times the derivative of cos x, u prime times v plus u times v primed. Now the derivative of 4 e to the x is 4 e to the x. So that's 4 e to the x cos x. The derivative of cos x here is negative sine x. So I'm going to go ahead and write this as minus 4 e to the x sine x. So this plus became a minus because the derivative of cos x is negative sine x, and 4 e to the x times negative sine x is negative 4 e to the x sine x. So I'm kind of doing a little bit of algebra there. We are looking for the slope of a tangent line, and we're looking for the slope of that tangent line at this point. The x value here is 0, so the slope of my tangent line is f primed of 0, which means I just need to plug 0 into the expression above. That's 4 times e to the 0 times the cosine of 0 minus 4 e to the 0 times the sine of 0. And just be careful with your order of operations. E to the 0 is 1, so this is 4 times 1 times the cosine of 0 is what? Who can help me with the cosine of 0? Is it there in the chat? Yeah, good, 1. Okay, 1. Minus 4 times e to the 0 again is 1. What's the sign of 0?
0.
Awesome. All right. So I've got 4 times 1 times 1 minus 4 times 1 times 0. That's 4 minus 0, which is 4. So my slope is 4. My point is 0 comma 4. So I write down the tangent line using the point slope formula. Y minus y0 equals m times x minus x0. That's y minus 4 equals 4 times x minus 0. Or just y minus 4 equals 4x. Or if you want to put it into y equals mx plus b, that's y equals 4x plus 4. Or again, you could stop here if you wanted. I don't care. Either one is fine. Okay. Questions on this one? All right. 7 is actually very similar. 7 is another product rule problem. So I think rather than doing both 6 and 7, which are both like find the equation of the tangent line to this product rule-y thing at this point, I'll let you guys work 7. If you want to see 7 done, bring it by an office hour. That way we can squeeze one. Oh, no, we don't. We're out of time. All right. We don't have time for one more anyway. I do see that there's still a handful of problems that we wanted to get to here. So if you guys want to talk more, come by my office hour this afternoon. I'll have a normal office hour this afternoon from 1 to 2. And then I will try to squeeze in an extra office hour. I know you guys' test is on Wednesday. So I will try to squeeze in an extra office hour to make up for the one that we missed last Friday before your test. I can't promise that it will be today. It will either be today or tomorrow, but I'll try to do it today. And as soon as I know where I've got time, I will make an announcement. Any burning questions before we go?
Is it okay if you record the office hours and post it, because I have a chemistry lab during that time, so I'll miss it.
Okay, yeah, and I do have another office hour from last week saved that somebody asked me to record and post. I've just been without internet for the last few days, so I will I'll get last Friday's office hour up, and I will record and post today's office hour as well. A quick note before we go, please look at the announcement I made this morning in Canvas. It has the instructions for exam 1, and you really need to follow these. This is very important. So make sure that you download and install Zoom on your phone. Make sure that you have Chrome installed on your laptop or PC or whatever computer you use. Make sure around 9:15 on Wednesday, you log into Zoom on your phone, and I'll post a link here, just like normal. But instead of going on your laptop or your PC, you need to come in on your phone. We'll get Zoom set up so I can see your desks and your hands. Then you're going to sign into HonorLock and start taking the tests. So please, please, please read these instructions. All right, if you have any questions, send me an email, come by office hours. Otherwise, I will see you guys on the morning of the test, right? I'll see you all on Zoom as we're getting things set up and making sure everything goes well, but please make sure you're prepared. Read the full announcement here. It's got a bunch of stuff in there that you're going to need. Also, don't forget to read the announcement that has the instructions for the study guide. That's important too, okay? Study guide 1, this has been up for about a week now. So please come back and make sure you read this. I want you guys to get credit. I want this all to go well. Otherwise, I'll see you in office hours or in the morning of the exam. Take care, guys. If you've already submitted your study guide, I will get you some feedback today, I promise. All right, take care.